Hi everyone, this is section 4 of chapter 17, and for this one we're going to be taking a look at hormone transport. And what this is once the hormones enter the bloodstream, we're going to talk about how do they actually move around inside of the bloodstream, how are they transported around. Now, what we talked about in section 3 is going to play a major role here because of the fact that we talked about what they were made of, and what they were made of determined whether lipid soluble or water soluble, and that is going to be a huge factor that's going to come into play. So we're going to be talking about that, and then we're going to talk about factors that affect concentration levels in the bloodstream as they're being transported around, and then we're also going to talk about something called half-life. So let's take a look at water-soluble hormones because they are really easy. Water-soluble hormones, since they are water-soluble hormones, they readily dissolve. If you think about the reason why, is because of the fact that blood, a major component of blood, is going to be water. So they're water-soluble hormones. So they can actually travel around freely, unattached, and go wherever they need to go. A few of them are going to use carrier proteins only to prolong their life. When they're attached to carrier proteins, that it actually helps keep them from being destroyed, which is what we're about to talk about with lipid-soluble hormones. But for this one, for the most part, they're roaming around freely in the bloodstream, going to where they need to go. Now let's talk about lipid-soluble hormones and look at this whole carrier protein thing a little bit more. So lipid-soluble hormones, because they are lipid-soluble, remember we talked about how lipid-soluble, one of the characteristics is they're hydrophobic, which again, well, most of the blood is water. So that means that they are pretty much scared of what they are going to be transported into or transported around in. So they are going to attach to a carrier molecule. Carrier molecule is exactly what it sounds like. It is a molecule that holds onto the hormone and it carries them around to where they need to go. And that's what that ferries the hormone. But it also is a nice layer of protection to make sure that they're not destroyed either. Some carrier molecules are pretty selective and they only bind one single lipid-soluble molecule, but some are non-selective, so they'll just transport anything around. They don't care. Let's take a look and see what this looks like. I'm going to kind of skip to a slide a little bit further down right here so you can kind of see what I mean. Look, there, that blue thing is the carrier molecule that I'm talking about, and there is the hormone that's attached to it. So it's going to go around in the bloodstream. When it gets to where it needs to go, it's kind of like a bus stop. When it gets to the bus stop, it is going to unbind from the bus and it's going to leave and go to where it needs to go. So at that point, it's going to be called an unbound or free hormone, and it will immediately leave the bloodstream and go to the cell that it needs to go to. It's not going to just wander around free in the bloodstream and just leave its bus and hang out in the bloodstream, again, because it would be destroyed pretty quickly and it wouldn't know where to go. So that's going to be your lipid-soluble hormones there. And that's what that means by bound and unbound or free. So as far as how hormones exerting their physiological effects, it really is going to depend on blood concentrations. And we already talked about how closely regulated glands are as far as it secreting hormones. We talked about how there's a hormonal stimulation that causes hormones to be secreted. There's that humoral stimulation where glucose levels, calcium ion levels, and things like that are going to cause a gland to secrete their hormones and the nervous system. So this is just kind of going in and talking about as far as hormone release. Once hormones are released into the bloodstream, so if you have a bunch of hormones released in the bloodstream, obviously that's going to increase the blood levels of that hormone, and vice versa. If the pancreas isn't secreting as much insulin, it's going to have a decrease in release, and that's going to lead to a decrease in blood levels. So as far as hormone elimination and how are hormones how do we get rid of hormones? They can't stay in the body forever. And we did talk about how some of them can last quite a while, some of them can last weeks, but they're not going to last forever. Let's talk about what happens to them. There's basically 3 routes that can happen. The liver cells can degrade them through enzymes. We can urinate them out through our urinary system, through the kidneys. That's how some hormones are picked up on tests, like a pregnancy test picks up hormones, and that's exactly how, because it's removed through the kidneys. But also some of the target cells actually take up the hormones as well, kind of like your neurons. Remember, neurons could do that reuptake. They could suck up the neurotransmitters. So that's a way to go in and decrease how hormone levels can go in and decrease. All of this is actually going to be tightly regulated by feedback loops. You might remember feedback loops, right? Most hormones are regulated through negative feedback loops. And we'll talk about these negative feedback loops when we get to insulin. It's a really good one with glucose levels and things like that. There's just a select few hormones that are going to be regulated through positive feedback mechanisms, and we will look at those as well whenever we get to it, or it might be later on in the semester when we get to that hormone. So now let's take a look at, again, continuing on with the levels of circulating hormones. Since we are talking about transport and hormones in the bloodstream, let's talk about how is it determined how long these hormones live? So hormones have something called a half-life. A half-life is going to be basically the time that's necessary to reduce a hormone's concentration to half of the original level. You don't have to get into the technicalities on what's going on here, but really what it is because steroid hormones are going to be on a carrier molecule, they're protected from destruction. So that means that most of your steroid hormones are going to have a little bit longer half-life. Like, for instance, testosterone is going to have a half-life of 12 days. Now, I think cortisol has a half-life. It's not as long. It's, I want to say that I read it was about 90 minutes. It doesn't sound very long, but if you compare it to some of the water-soluble hormones that only last a few minutes, then it's a little bit longer than that. So water-soluble hormones are going to have a shorter half-life, so a few minutes for these small peptide hormones. What that means is that water-soluble hormones have to be replaced more often if you think about it. If they're being destroyed, or if they are going to be reduced in half through a certain amount of time faster, then you're not going to have as many. Let's say, an hour from now, you're going to have to produce more of them more frequently. But if you have something like testosterone that hangs around a little bit longer, say for 12 days, you don't have to, the organ does not have to go in and produce as much of that hormone as possible. So that is going to be half-life. So what we're going to move on to next. So we basically talked about how hormones are going to circulate and transport around into the bloodstream. The reason why they're transporting around is because they're looking for a target cell. That's our next step, is going to be what happens once it gets to the target cell. What does it do? Again, this is going to depend on whether it's lipid soluble or if it's water soluble, because one of them is going to be able to easily go right through the cell membrane. One of them is not going to be able to get in at all. So that's going to be the next section. Until then.